Today is March 19. My name is NerimanAKC A. My student ID is 230914400027. First, I am showing the network topology in the NED design view, and here is the configuration A. This topology contains hosts, switches, routers, a configuration module, and visualer module. The hosts represent the device, represent end device. The switches connect local device, and the routers connect different network segments. The configuration module is responsible for assigning IP address and creating routing information automatically. The visualer module is used to display and observe the network during simulation. And here we can see the source code of the network. This code defines the structure of the network programmatically. The submodules represents network components such as hosts, switches, routers, the configuration, and the visualer. The connection section defines how these components are linked to each other. This is important because the simulation uses this structure to model communication and routing behavior. Also, inheritance is the concept of creating new modules or classes by extending existing ones. In OmNet++ and the iNet framework, many modules such as routers, hosts, and switches are built on reusable base components. This makes the design modular, easier to maintain, and more scalable. In other words, inheritance helps reuse code and behavior instead of defining everything from the beginning. Then let's open this, and here is the config steps. This file defines which network configuration is executed and which parameters are used in the simulation. It also contains the step configuration such as step 4, step 5A, step 5B, etc. In addition, XML files are referenced here to define addressing and routing rules for specific steps. Let's run as OmNet++ simulation. And start with step 4. Step 4, introduce fully automatic static routing table configuration. In this step, the IPv4 network configuration automatically assigns addresses and creates routing tables based on the topology. Compared to previous steps, step 4 focuses on automatic routing table generation instead of only basic address configuration. The main purpose of this step is to reduce manual configuration and avoid addressing and routing errors. At this stage, the routing information is produced automatically from the existing network structure. And stop simulation. Then go to routing table. Not here. not here too. Yes, here. As you can see, here is the routing table. This table shows how packets are forwarded in the network. Each row represents one route. The destination field shows the target network or host. The net mask field defines the size and boundary of the network. And zoom in. The gateway field indicates the next hop to that packet should be sent to. The interface field shows which outgoing port is used to forward the packet. The routing table is formed automatically by the configurator to the network topology and path calculation. And the net mask is used to separate the network part of an IP address from the host part. It's essential for subnetting and for identifying whether a destination is in the same network or in another network. For example, the router uses the destination address together with the net mask to determine the correct route. And the gateway is the next hop used to reach another network. And if the destination is not directly connected, the packet is sent to the gateway. In routing, the gateway is a critical value because it tells the routers where to forward the packet next. And the interface is the communication port through which packets are sent or received. It may represent an internet connection or another network connection point. In the routing table, the interface indicates which output link is used for forwarding. Let's config step 5A. It is introduced manually overriding individual routes to specific hosts. Compared to step 4, where routes are generated automatically, step 5A adds manual control for a particular destination. This means that even if the system can calculate routes automatically, we can explicitly force a chosen route. The purpose of this step is to demonstrate how routing decision can be customized when needed. Then stop it and config step 5B. This step extends the previous step by overriding routes for a set of hosts instead of only one host. The difference from step 5A is that now the manual rule is applied to multiple destinations. This is useful when a group of devices should follow the same routing policy. The goal of this step is that to show routing behavior can be controlled not only for one device but also for a subnet or a host group. And in step 6A, It is introduced metric-based routing using data rates compared to step 5b. This step doesn't only rely on automatic or manual overriding paths, but also evaluates the quality of links. In this step, the fastest path is determined according to link performance, especially link speed or data rates. And this means that the selected path may not only depend on topology, but also on how efficient the links are. And also, it is the shortest path is determined based on the topology of the network. In general, it means the route with the minimum number of hops or the minimum routing cost according to the configuration logic. In this tutorial, the configuration automatically computes these routes and fills the routing table. And so the code responsible for the shortest path behavior is mainly the configuration logic and configurator logic defined through the tutorial configuration and the net routing mechanism. And the other step 6e step 6b introduce manually specified link cost compared to step 6a where data rate is used as the matrix. Here the route is selected according to manually assigned cost. This allows the designer to influence routing decision directly. The purpose of this step is how to administrative or logical preferences can be used in routing, not just only physical speed. The fastest path is determined according to performance-related criteria such as bandwidth, delay, or link cost depending on configuration. In step 6a, the routing decision is influenced by the data rates. In step 6b, manually defined link costs are used. Therefore, the fastest path is not always the same as the shortest path, because a path with more hops may still be faster if its links perform better. And stop this simulation and go back here. And here the code section of this project can be explained in three main parts. First, the NED file defines the topology and the structure of the network. Second, the omnet pp INE file defines which scenario is executed and which parameters are used. Third, the XML files define addressing rules, route overrides, and other configuration details for specific steps. And together these files define both the structure and behavior of the simulation. And 1 minute. The simulation works as a discrete event simulation. And zoom in. This means events are processed one by one in time order. Packets are generated, forwarded, and received according to the routing logic and protocol behavior. During the simulation, the configuration first prepares addressing and routing information. Then the host and routers use this information to communicate. This simulation is visual through Qt environment which provides a graphical interface where we can observe modules, links, packets, flow, and the internal structure of nodes. This visualization is useful for understanding how routing and forwarding happen step by step. And also I want to mention authorization. In this tutorial that is not implemented as user authentication. Instead, communication behavior is controlled by configuration rules, addressing, interface, and routing policies. In other words, the simulation controls which node communicates with which destination based on configuration, not by username or passwords. And when we building a network, several important issues must be considered. We must avoid IP conflicts, define subnets correctly, choose suitable net mask, configure gateways properly, and assign interface consistently. We also need to consider scalability, routing efficiency, delay, bandwidth, and manageability. Good network design improves both performance and reliability. In conclusion, in this tutorial, demonstrates how network topology, automatic configuration, routing tables, routing overriding, shortest path calculation, and fastest path calculation selection work together in Omnet++. And as I mentioned, step 4 focus on automatic static routing table generation. And step 5a and step 5b demonstrate manual overriding for one host or for a group of hosts. Step 6a and step 6b introduce metric-based routing using data rate and manual assign link codes. And overall, this tutorial shows how efficient and flexible network configuration can be achieved in Omnet++. Thank you for watching.